Good afternoon, everybody. My name is Olivier Giroux. I am an architect at NVIDIA. I design GPUs. What do I have to do with C++? Well, I'm also on the C++ committee. I'm the chair of Study Group 1, which is a concurrency and parallelism study group. Okay. So I chose this title of High-Radix Concurrent C++ because I was thinking about two things. I was thinking about high-radix data structures, trees with large fan-outs. And I was thinking about high-radix threading models, groups of threads and groups of threads that themselves involve large numbers. Groups of 256 groups of 256 threads is a perfectly normal thing in my world. So I was thinking about these two things together, and I wanted to show you something that I think would surprise you. All right, so the big spoilers is we're going to talk about GPUs. You're not surprised. Okay, so last year I gave a talk about the design of Volta. Volta was our big supercomputing architecture that we launched last year, a data center architecture that we designed with C++ in mind from the get-go. There are large parts of the design that we completely replaced. And as we were designing the replacements, we would occasionally quote the C++ standard at one another. So that's how much of an impact our thought for C++ had. Okay, so we refer to our architectures for compute as having a capability level. Here I'm saying that Volta has a compute 7.0, compute 7.0 capability level. And that introduced a number of cool things that you may or may not have heard about. Okay, so the first one I'm pretty sure you've heard about, and that's our fused MMA operations. It used to be that fuse FMA was a big thing. Is your code ready for FMA? Nowadays, we're really looking at fusing matrix multiply operations to accelerate matrix multiply much more. Okay, so that was definitely the biggest headliner of our launch for Volta was our 4x4x4 matrix multiply hardware. Okay, but there were other cool things in there that are particularly of interest to C++ developers. And so two examples of that is that we added support for starvation-free algorithms, which are going to make a showing in this talk. And we redesigned the memory model for C++ 11. Okay, but last year, that may have felt pretty distant and academic for a lot of you. Volta GPUs, although they're available to the mass market, they're fairly expensive. And a lot of them went to data centers or supercomputers. For example, this is a picture of Summit, the world's fastest supercomputer, which is built on Volta. There was a big news that was coming this year that I've known all along, obviously, was coming this year. The big news is that this year we followed up on Volta with a new architecture called Turing. You have probably possibly heard about Turing. You've possibly heard that Turing includes ray tracing acceleration, which is super cool, and I'm stoked about. But there's something you may not have heard. What you may not have heard, actually, is that Turing includes all of the improvements from Volta as well. So Turing is Compute 7.5, and Compute 7.5 is a strict superset of Compute 7.0. Now, that starts to be a really big deal for all C++ developers, because a lot of you will come to own one of these. Like you might buy one because you're building a gaming rig. Or eventually down the line, they'll be available in many more systems. And so it's possible that you'll just come to own one of these. It's great at C++. You're a C++ developer. You should run C++ on this. All right, so I'm going to tell you what you can expect and how much fun that's going to be, actually. Okay. So I was thinking about this much earlier in the year. I knew Turing was about to hit shelves around CppCon. And so I was thinking, what would make a completely unexpected demo? Something I could show you and you'd be like, wow, I didn't expect GPUs to be good at this. Okay. So what do people think GPUs are good for? By the way, this is not This is me making a guess as to what people think, or talking to people to know what they think GPUs are good for. I think GPUs are good for many more things. All right, so what do people think GPUs are good for? People think, when people think GPUs, they think floats, little floats, big floats, doubles, double the scientific computation, complex doubles. People are thinking arrays. Like they're thinking, I know when GPU came out, you would allocate large buffers and you would move these large buffers and coarse-grained data movements. Okay, so I'm thinking floating point data, I'm thinking large arrays, I'm thinking highly regular memory access, adjacent threads accessing adjacent memory locations. And I'm thinking, when I put my C++ SG1 hat on, I'm thinking lock-free algorithms. I can't actually write arbitrary synchronizing code on GPUs because if I write a lock, for example, and you could search for that on the web. If I write a lock, for example, I might expect GPUs to have problems with that. What do people think GPUs are bad for? Well, have you ever heard of anybody doing string processing on a GPU? Probably not. What about node-based data structures? Trees, large trees. What about random memory walks? So I go to memory and it's just a total scattershot. There's like not going for adjacent locations. Do you have a question? Oh, you thought of strings? Oh, good. Good. How about starvation-free algorithms? Algorithms that, for example, polling on a memory location with potentially contention with other threads. You're waiting for a thread to set this location, but you don't really know which other thread is setting this location. It might be in the same group as you or in a different group. Okay. I think most people think the GPUs are bad for this. Thanks to the peanut gallery. So I'm thinking to myself, let's build a trie. Let's go build a trie. All right, let's do that. So what's a trie? So a trie is a node-based data structure. I most often refer to it as a radix tree. So it's a tree with a large fan-out, not a binary search tree, that encodes that is essentially a map where the keys are not stored in the tree. The keys are the location in the tree. Okay, so for example, if I wanted to make a map of strings to something, I would have a root node, which is an empty string. Then I would have a first level of nodes, which is is indexed by the alphabet of the first letter in a word. And then after that, there'd be another node with the second letter of the alphabet, and then another node with the third letter of the alphabet, and so on. Okay. So radix 26, that's high, hence I got a talk title. And like I just said, you can implement a map, conceptually, a map of string to something using this data structure. And in this demo, in this talk, that something is going to be a count. It's going to be we're going to compute a word frequency over a text corpus by inserting into a trie data structure and incrementing the count as we find or insert nodes into the trie. Okay. So this is sort of an interview question type of problem. What might our code look like? So here's a summary of what my data structure will look like and how I index it. And after this, we're going to look at the algorithm. This isn't supposed to be a trick question. It's not supposed to be complicated. It's just a sequentially building a trie. So here I've got one type of structure, trie. Each node of a trie is itself a trie. I have 26 down-level references that are each one a pointer to another trie. And each node gets one of these counts. This helper function here is going to take some character, not a Unicode character in this case, but it's going to take some character, and it will compute the index into the fan-out of the tree. And I'll return -1 when it's not an alphabetical character. It's not very complicated. I am not looking to make a thing of beauty of this. It's just a simple version of this. Okay, how do we make a trie? Well, this is going to be sort of the heart of my code base here. The make trie function takes a trie to insert into. For this example, it's going to start out empty, but actually for the algorithm, it doesn't need to start out empty. It could be, you could think of it as append to trie. I'm going to make a bump allocator, which is a pointer into some pre-allocated range of trie nodes. I'm taking allocation out of this problem. We're only going to look at the main algorithm. Okay, so that's going to be my bump allocator, a pointer into a range of free nodes. And then a begin and end into a character sequence, which is going to be the text corpus that we'll find words from. Okay. The algorithm itself is not super complicated. Basically, we start at the root node and we walk characters until we, so for each character, we pick a subnode of the node we're looking at. We're going to keep going like this as long as we don't find a space or a non-alphabetical character where the index will be -1. At that point, we say wherever we are in the tree, we increment the count there and reset to the root. If there is no node for the node we're looking for, then it'll be null, and we'll just bump the bump allocator and assign that pointer to that place in the tree. Okay. Not too complicated. I want to point out that all of the code in the stock is going to be available on GitHub at the end, so don't worry about it. You can check it out after. Okay, so let's go run this. And this is the part where we attempt live demos. So I have 3 systems here that are standing by to run this demo for me. Here I've compiled in the sources that are available with the stock. I've compiled trie-st, the trie single-threaded, which is exactly the code I just showed you. And I can run this over a number of books that I got from the Gutenberg project. This is these text files. They come by just w-getting books from the Gutenberg project. So here I just did this on my laptop right now. I have another system over here. Run this. It's a lower clocked system, but it has many more cores, and that's going to become important in the next demo. Okay. All right. So on the system that has the many more cores that we're going to use for the other demos, which is the specs are down here, it takes 68 milliseconds to do this, 1 thread. Okay. Well, obviously we're going to multi-thread this. We're going to go to the SG1 version of this. Okay, so how are we going to convert our sequential version into a concurrent version? There's a couple of things that we have to do. One of the first things that we have to do is that we have to realize that we're now going to be concurrently accessing the trie, and actually there's no member of the trie that we will not access from one thread or with interlock. So we're actually going to make the count atomic, and we're going to make the pointers atomic, and we're going to eliminate insertion races by using an atomic flag. And the algorithm is going to be on the next slide. There's 2 more things we need to do. We need to realize that the bump allocator will also be used concurrently, and so we're going to make that one an atomic as well. And then finally, there's something pretty fundamental about making the multi-threaded version, where I'm going to invoke this make trie function in multiple threads. They need to know which thread they are. So each one is going to receive an index that says which thread ID it is within a domain, which is the total number of threads that are going to be running this algorithm. Okay, this part so far is pretty simple. There's more complexity in how we go about implementing the algorithm. Okay, so we're going to do it in 3 easy steps. First step is there's going to be a part of our program that is going to split the input range into a bunch of strips. We're going to do this relatively crudely, let's say. We're going to take the whole input, the whole text corpus, and we're going to slice it into domain number of slices, and then each thread will go access the index numbered slice within the domain number of slices. Okay. So we're going to do that. But there's a trick when you do this. Now, the boundaries of these slices for the input, actually some of them fall into the middle of a word. So what we're going to do is either as a pre-adjustment step or as part of how the algorithm runs, we're going to adjust the strips start and end to start at the next word and end at the next word with treatment of the boundary conditions where you start at the beginning and you end at the end. Okay, not too complicated. All right, finally, we need to, we can run the same code as a sequential version, except that insertions now are concurrent, which is why we made the members of the Trie structure atomic. And so we're going to run code like this. Okay, so this is just replacing the node insertion part. We're going to check if the pointer is null. And if it's not, then we're good to go. We can just use that pointer. We just read it at the bottom. If it is null when we get there, then one of the threads has to be elected to go do the insertion. And that's the test and set that is right here. Okay, so this test and set determines if you're the first person to arrive, if you're the first thread, to arrive to insert the node. And that tells you to go do it. Okay, that sends you over here. So that's on the false, right? If the previous value of the flag is false, then you take this branch and you're the one who's the first one. And then you do essentially the same thing as the other slide, except just atomified. You know, we used to increment and then assign, so we do this again. We fetch add and then we store. Okay. Now, when we store to the pointer, that will tell the other threads, the one that lost the test and set and went into a spin loop, waiting for it to become non-null, that permits those threads to make more progress now. Okay, this is where this becomes not a lock-free algorithm, but a starvation-free algorithm. And that's pretty important because it was very natural for me to make this step here. It was very easy for me to deal with the racy insertions into the trie by using the spin lock approach. This spin lock approach is not a major concern because we know that, first of all, the odds of reaching the spin lock are very low. And then when you reach the spin lock, you know for sure there's another thread that's going to set this pointer to non-null very soon. So it's not really a question of performance or a question of system load. I'm not very concerned about the presence of the spin lock on that basis, but I am concerned, both as a GPU architect and as a member of SG1, I am concerned that now this algorithm is fundamentally different from other algorithms I could have chosen here. Now it's a starvation-free algorithm. It requires a benevolent scheduler for this application to make progress. And you can learn all about that by searching for On the Nature of Progress. Okay. We're going to talk about this again a little bit later in the context of GPUs. Okay, so let's just go and run this. Well, I can run this on my laptop right here. There's a couple of things that just happened. Oh, my laptop does not have 40 cores. We're logged in somewhere now. So I can run this on the same system where I ran the single-threaded version. There's two things that you can notice. Well, one is that actually, if we run the multi-threaded version in single thread, we slow down. And that's to be expected. It's to be expected for a few reasons. One, the code generation is not as good as the original code generation because now we have atomics and we have releases and acquires, and there are fewer optimizations that the compiler could do. Still can do many, but not all. In this example here, actually, we did spin a thread. We spun up one and then we joined it, but we did spin up a thread. So we slowed down in single-threaded execution mode, but we did net a speed up. So that's pretty cool. That's pretty cool. And the results are not completely repeatable. You can see that it bounces around. And I guess here we could try it on my laptop. So interestingly, my laptop and that machine sort of solved the problem in about the same time. Well, no, but there's a reason. That other machine is a large Xeon with lots of cores. It's clocked lower. Of course, it's got a beefier memory system, but it's clocked lower. my laptop here probably just boosted to its max clock for a short amount of time. Okay. So in some run, the stability of the run is a little bit annoying, but in some run I got these numbers. And we did net a speed up. You saw the other numbers, so you could see what the nature of the speed up looks like. So we did net a speed up. I mean, we didn't quite strong scale here, but we got a speed up, so that's good. I feel like the small amount of effort I put into this paid off. Okay. Cool. All right, so we check tens of threads. How do I get to 100,000 threads? What do I have to do to run at that scale? Well, yes, you answered that question. GPU is the answer, yes. Okay, but concretely in code, what do I have to do? In the previous couple of slides, I showed you some code. Yes, we could have spent more time looking at it, but I need to press on. Okay, so what's the CUDA code here? Do you all know CUDA right now? I don't know. Oh, well, that guy does. That guy does. Oh, no, you don't need to all tell me. Many of you know CUDA. But I'm up here and I'm thinking, oh, actually, it's really not a given. So here's a crash course. Here's a crash course. You right now are going to take a 10 or 15 minute crash course in CUDA. Are you ready? Let's do it. All right, so what's CUDA? CUDA is an integrated heterogeneous parallel programming system for C++. It's really important to know that it is not C++. It's a programming system that includes C++ as one of the elements, and it certainly is the central element that it is built around. What else is important to know? Well, I said heterogeneous. Well, that means that it accounts for both the host CPU and the accelerator, the device. And what do I mean by integrated? I mean that you write one source code. You don't write a host program and an accelerator program and then pipe the inputs and outputs from one to the other. That's not how CUDA works. In CUDA, you write essentially one code base, and it's all in C++, and all the functionality interacts in a tightly integrated way. Okay, so what's the programming abstraction to this? Like what does CUDA look and feel like in short? So the model is that there are some functions in your program that you're going to call with very large numbers of threads. And when I say practically unlimited, what I mean is that when you launch threads on CUDA, you will give it sort of an index space that could be one-dimensional, two-dimensional, or three-dimensional. And in the case of three-dimensional, it's like 64 bits three-dimensional. So the number of threads you can express is extremely large. Obviously, the machine cannot run a 64-bit number of threads. You can't do that. But you can launch, you could, for all practical purposes, map the index space of your problem to CUDA. You do not need to be in charge of dicing up the different threads and manually managing the threads. If you have a problem and your problem measures 100,000 by 10,000, you can express that to CUDA, and then CUDA will launch the tasks, and they run for the amount of time that it takes for the computation to finish. And obviously, GPUs being used in HPC, some of these computations can take a long time to finish. Okay, so select functions, not all of the functions, select functions that you select. That can be called by practically unlimited number of threads in groups of up to 1024. You decide how they're grouped, but the maximum group size is 1024 with some constraints, which I'm going to replace by details, with some constraints. And if your program stays within the constraints, then your program will see consistent memory at all times. Okay, so what are those constraints? So in CUDA 1.0, which is the model that a lot of people initially heard about, that you CUDA malloc and then you get a separate pointer. The CPU can't touch that, and you CUDA memcopy, and you have to memcopy in and memcopy out and all that. That's back to CUDA 1.0. But from a model perspective, it's parallelism which is the absence of interdependencies between tasks. Okay, so you express a number of tasks and you vouch that they are independent, because that's parallelism, and asynchrony, where you express these tasks. Not only are they independent between one another, but a dependency on these tasks need to be expressed explicitly, so therefore they can begin executing concurrently with your CPU thread. Okay, that's between groups, and then within a group that can be up to 1024 threads, you get a guarantee of concurrency. That is, these threads in fact can interdepend. The threads within a group can communicate with each other. Okay, so you launch groups that are tightly knit and can communicate, and these groups between themselves are loosely knit and they cannot communicate. Okay, so that's the CUDA 1.0 model. The CUDA 10.0 model, 10 years later, basically, is that it's that model from 1.0, but we've also added the ability for these groups of threads to loosely interdepend as well. So that's, we got a lot of mileage out of this model because we didn't completely change it, right? We clarified that they can also communicate with a clarified progress guarantee. Okay, so why parallelism? Well, it's because you get fewer bugs and higher performance just by default. Of course, when you vouch that your tasks are independent and it wasn't quite true and you wish that they would communicate, then you have to do a lot more work, of course. But as a baseline, you get fewer bugs and higher performance. And then why did we reintroduce concurrency? Well, it's because actually if you get dirty a little bit, then you can get higher performance. And so just like C++, CUDA C++ doesn't judge if you mix paradigms. It's parallelism and asynchrony and concurrency and consistency and the progress all in some measure all together. Okay, now one thing I want to emphasize is that CUDA C++ is always a superset of C++. It's always a superset of C++ because the host CPU never loses anything. When you go to CUDA, you never need to give up anything. All of your CPU code still can do everything your CPU code used to do. It has access to all the libraries it wants. It has access to all the features of the language. Okay, some of the features then also extend to other processors, and this is sort of how things are divided up. So there are things that only the host processor can do, the things on the left, throw in anything to do with exceptions, anything to do with RTTI and TLS. There are things that both processors can do, but the processors need to do it in isolation. What I mean by that is you can make polymorphic objects, you can construct them on the CPU, and the CPU can use those, and you can construct them on the GPU, and the GPU can use those, but you can't pass a polymorphic object from the CPU to the GPU. And all three of these are essentially because there's some notion of there being a pointer to the ISA code encoded in these things. And obviously, the CPU can't execute the GPU code, and the GPU can't execute the CPU code. Okay, so beware. And then finally, in the third column, you have what all processors can use, and they can use together at the same time. That is, the CPU can construct an object with certain features and just pass it to the GPU, and the GPU will understand what that object is and implement those features faithfully. And that's basically the rest of C++. And then the point details are at this link. Okay, there are 9 extensions we're going to need, 9 things that are not in C++ that we're going to need to be able to read the demo code today. Okay, 9 things. Those 9 things are, we're going to have some memory management APIs. They're a lot simpler. If you dabbled in CUDA before these were added to CUDA, these are much simpler than what we used to have. Okay, so CUDA malloc manage and CUDA free, they'll implement a symmetric heap. What I mean by that is you allocate memory into that heap, and the CUDA driver will make sure that the GPU and CPU have a consistent view of these. Without you doing anything else special. You don't need to do memcopies. You don't need to do CUDA memcopies with that. You just malloc. You do what you do on the CPU, you do what you do on the GPU, it works. We'll use CUDA memset because actually CUDA memset can zero memory like a hero. It's because there's fixed function hardware on GPUs that's exceptionally good at copying memory, yes, but we're not going to use that feature, but it's also exceptionally good at zeroing memory. So we're actually going to use this in this demo. There are some decorations we're going to need to put on our functions, and I'm going to show you what to do with that in the next slide. CUDA device synchronize is how you resolve the asynchrony of executing CUDA threads. I said that in CUDA you can invoke functions in many threads asynchronously. Well, CUDA device synchronize is the function you call when you need to get the result. There's the infamous triple chevron call that when we call a function and put the triple brackets, that's going to call that function on the GPU in that many blocks and that many threads. And then here we're going to have our indices, which play the same role as in our CPU example. We had index and domain. These will help us work this out. OK, so here's an eye chart, and we're going to dice it into little pieces, one at a time. OK, so host device is the decoration you put on ordinary functions. There is a lot of code in the world, a lot of my code, a lot of your code. There's a lot of code in the world that can just be annotated with host device. It just has to not use RTTI and not throw and carefully use function pointers. Assuming that you meet these, that can be host device. OK, so this is my ordinary function that does nothing interesting. Entry points into the GPU have to be marked with global. Those are just entry points, though. Global functions can't call global functions. The only thing that can call a global function is the CPU, and it can only call it with triple brackets. OK. So our entry point is going to be marked with global. There's a gotcha you got to be aware of. You guys are sophisticated C++ people. You need to know that when you pass operands to a global function, they are assumed to be trivially copyable, whether it's true or not. So be careful. All right? We're going to use the manage heap in this demo. So in this demo, what I did is I made an allocator. This is just an allocator. And basically, there's only two lines of it that are interesting, CUDA free and CUDA malloc manage. The rest is just filling out the allocator boilerplate. And that eliminates a lot of tedium. We can use triple bracket on a global function. In fact, we must use triple bracket on a global function. Here, I'm just going to launch it with one thread. Calls to triple bracket are asynchronous, so we need to call device synchronize when they're done. Because my ordinary function is marked host device, the host can call it too. And so I can, for example, just call ordinary function on the CPU side. That can be really convenient. Different people have different workflows. My personal workflow is I tend to write all of my solver or my model or whatever it is I'm working on in host device code. And then I get a lot of mileage out of running it on the CPU for a while. And then I take it to the GPU knowing that it's already kind of pretty good. And then I do that next step of finishing my GPU tuning, for example, that way. It's just a way to work. It's up to you. OK, so that's the cheat sheet using each of the 9 things once. OK, but that's not actually a trie solver. That's not what it does. It's just the cheat sheet. We can take a look at CUDA on Godbolt. For example, if I put my cheat sheet program into the compiler explorer, I get access to CUDA now on the CUDA Explorer, on the compiler explorer. Yes, starts with C. And here I have it running with NVCC 9.2. I can also run it with Clang. And what I see here as the assembly is NVIDIA's PTEX assembly. So you can take CUDA code and put it on the compiler explorer and take a look at what the generated NVIDIA intermediate assembly looks like. This assembly is the same one that's documented at the PTEX manual, available on our website. You can download it. And special shout out to the memory consistency model, which I love. OK. You'll need coffee to read it, though. OK, so all right, now that we've done this, now we know CUDA now. Cool. Now that we know CUDA, what's the Trie demo, what does the Trie demo look like now? I did all the decorations, so am I good? No, there's more decorations, this is just the algorithm. Am I good? Well, actually, I have some more details to give you. The more details is that I didn't tell you what happened with the library. So if I revise my previous slide, what I should have pointed out is that everything in STUD can be used by the CPU alone. And what can be used by both processors all the time is the rest of the C++ language. Okay. What we need for this demo is access to a freestanding library. Okay, the standard recognizes two subsets of C++. One is hosted, which means everything, the subset meaning everything. And the second subset is freestanding, which is an implementation-defined set of headers, but at least the ones in table 16. Okay, and the ones in table 16 are very basic things, but that includes atomic, which is what we need. Okay, so what we're going to do to run this demo on the GPU is that we're going to use my freestanding library. And I put it on GitHub, and put it live today. You can try it out. You should read the README, though. Okay. All right, so now we have a freestanding library here, which all processors can use. And it puts standard definitions of symbols in the SIMT : stud : namespace. All right, so now we're going to look at our CUDA C++ version. What do? Well, we do the 9 things. We do the decoration. So we put host device on our solver, and we do the other things with the managed allocator to allocate the memory and whatnot. Okay. We convert our stud atomics to SIMT stud atomics, and also that one. And we're done. Now we've ported it. Okay, so let's go run that. And obviously I cannot run that on my laptop, but we can run that on this system over here. And that will spoot up the CUDA driver, and this will run, thank you. And boom, there we go. Well, that's pretty cool. That app now came up. It ran in 163,000 threads, and it ran on the system when cold about 5 times faster, and when the system went hot about 10 times faster than what the 40 threads were able to do on the Xeon before. We can also do the same thing on a different system. So the other one was a big, beefy server type of machine. This one here is just my desktop at the office. Works just as well. All right, so let's get back to the show. All right, so I averaged all of the run numbers, so let's say 3 milliseconds. That's pretty good. You know, that was pretty low effort. Once we got a freestanding library, that was pretty low effort. Yeah. Right. All right, so 100,000 threads, check. Okay. But what just happened? You know, I thought GPUs were terrible at this. Okay, so a little bit more details about the performance. Actually, the computation took even less time than you think. It took about 650 microseconds for the GPU to build the Trie. And then the rest is the overhead of getting the data over there and back over the PCI bus, and some control overhead. The ratio of overhead to computation gets worse with smaller problem sizes and gets better with larger problem sizes. You could commonly, for example, if you're doing a lot of processing, you would commonly overlap transfers with computation so that it amortizes out to just paying the 650 microseconds. But again, it was supposed to be terrible. Why wasn't it terrible? Well, the reason is this application's probably memory latency bound pretty much everywhere it runs on CPUs. It's chasing over memory. It's being pretty chaotic. It's not very predictable. But if you throw 100,000 threads at a problem, the exposed latency pretty much disappears. And at that point, when the exposed latency disappears, you just become bandwidth bound. And there's a lot of bandwidth on GPUs. You know, the memory bandwidth of the GPU we ran on is something like 900 gigabytes per second. A very expensive CPU will get you, I suppose right now is like 50 or 60 gigabytes per second. Something like that. It's a lot more memory bandwidth. Okay, now can any GPU run this demo? No. They cannot. And actually, that's kind of why I'm here. That's what's cool about the launch of the new Turing GPUs, is that there's only a few GPUs that can run this. There's our large data center Volta chips. There's our embedded AI driving platform Xavier that can run this, but it's not available in your hands yet. And Turing. Pretty cool. Okay, so only these will run this because we have a starvation-free algorithm. And if you were to take this algorithm and run it on another GPU, then what would happen is it would hang. Now, maybe we could dig ourselves out of this hole by throwing more complexity at it and imagining a different algorithm that is potentially lock-free and all that. But you know what? That would be more effort. And a big part of my point here is that actually that was fairly straightforward with a freestanding library. Okay, so pretty quickly, I wanted to tell you guys something about C++20. Because that's one of the things I'm trying to deliver to you guys. That would be great with the rest of SG1. Okay, so there's this part which wasn't great. We did have a spin loop in there. Again, I explained that spin loop is probably okay, but in general, good polling loops are very difficult to write, and so we end up with only terrible polling loops in everyone's code bases. So in C++20, we have a new facility that's going to make this much easier. We're going to have essentially an abstraction for polling loops called atomic weight. And here is atomic weight explicit because it takes a memory order. So it replaces the polling loop with this polling abstraction. It is paired with a notify, which is somewhat similar in concept to waiting on a condition variable and notifying a condition variable. And the reason that we need a notify is because the idea is that this is going to probably be implemented using, say on Linux, futex. Ultimately, initially polling a bit, and then eventually maybe yielding or sleeping a bit, and then after you've failed for a while, you should probably come to full rest into the kernel. You call futex. But if inside of atomic weight there's a path that leads to futex, then you also need a futex wake, and that's what's going to go into the atomic notify. Okay, so that's one thing. There's a number of other things. I probably don't really have time to talk about them in great detail, but I'll tell you one thing about each one. We're going to have an auto-joining thread with interruptible waiting. That's cool. We have the waiting functions that I just talked about. We'll finally have semaphores. Finally. We'll have latches and barriers, which are cooperative synchronization primitives. Latches are one-time use, fan in from multiple threads. Barriers are multiple use, fan in and fan out between multiple threads. We have atomic ref, which is going to allow you to do atomic operations on non-atomic variables. One of the cool things about that is it will actually help port code that has crusty old C code in it, that just has volatile end pointers or something. It's dirty. I don't like it. I don't like volatile end pointers for synchronization. It's in people's code. It's a reality. Atomic ref actually will make these code bases be easier to be brought into the modern present. Okay, unseek is we're going to have a simple and effective vectorization policy. We have a bunch of improvements to atomic flag and whatnot, and we have some repairs to the memory model that are in flight. All right, so to wrap this up, Turings are shipping by now. You, all people, should try them. You should try C++ on them. And if you try them, we'd like to hear back from you, definitely. Okay, and today's code is available at this link. And that's it. I think we have a little bit of time for questions. Thank you. We'll stretch into the next 5 minutes, I guess. The next talk probably starts at 15. Hi, Billy.
Hi.
Hi.
In your atomic notify all example.
Yes.
Because do you need to be worried about spurious weights on the spinning side?
It's perfectly valid for the spinning side to experience spurious weights. In fact, it doesn't promise to go to sleep, and it doesn't promise to not go to sleep. So it.
What does that do to your try
It does nothing bad to my try demo. The atomic weight does not return early. So it can wake internally, but it needs to retest the memory location. And if the memory location has not been updated, it needs to sleep again.
I see. Thank you.
Yeah.
We actually have 15 minutes.
We have 15?
Of the session.
Okay.
Your hour started at 15 minutes.
Oh, yeah, thank you.
Hi.
Hi.
So I want to ask about how efficient about the CUDA model about the resource synchronization between the GPU and CPU side, because I know for DX11 or something before OpenGL, you kind of have like a big overhead between the state machine synchronization between GPU and CPU, that kind of things.
Right, right. So there's a lot of different reasons why various versions of DirectX in the past experienced high overhead. Like, for example, there were many generations where almost every call was a kernel call and not just a user mode dispatch. There is quite a lot in CUDA that is simply done in user mode and doesn't need a kernel transition. So the efficiency is, it approaches basically just the efficiency of signaling over the PCI bus. And then the dominant factor in how expensive it is for you to go to the GPU and back is really how much data you're referencing. So if you need to reference a lot of data on both sides, then that data has to move. Ideally, what would happen is you would move your data to the GPU and try to keep it there as long as possible. And if you have multiple computations, you try to keep your data there. Even if the control comes back and forth, you try to keep the data there so it doesn't take time on the PCI bus.
So that's the gap and scope thing which control, right? Like this is run on GPU and this is run on CPU. So
right.
Do it by batch-ish, that kind of feel, right?
Right. So the code. So you're in control of how the code moves back and forth.
Okay.
Definitely. If you use the managed memory allocator, then CUDA is in control of how the data is moved. But you can. If we were to get into a tuning discussion, there's a lot of hints and knobs you can use to say, well, this data everyone can touch, but usually the GPU touches it. And then CUDA takes that into account when it decides where to put it. And then in the extreme end, you can still write CUDA 1.0. Like you still can go back and say, well, for most of my data, I let CUDA decide what to do, but for this piece of data, just this one, I'm going to control it. And so at the sort of high end of performance tuning, you have full control.
Okay, thank you very much.
I have 2 questions. The first one is, how do you debug this? And the second question is the memory order constraints.
Yeah.
So x86 is always sequentially consistent.
No.
Well, most of the time.
No.
Okay. But on ARM, it matters, was what
Yes.
I'm saying. But on x86, it usually doesn't matter.
Okay, all right. How do you debug this? To your first question. How do you debug this? Actually, you debug this the way you would normally debug this, which could mean different things. If you're a printf debugger, we have printf, so you can do that. Of course, printf from hundreds of thousands of threads could be very impressive. Okay, but more seriously now, CUDA comes with GDB. It comes with CUDA GDB. It comes with a GDB that does everything your normal GDB does, but in addition to what it normally does, you can backtrace and set context and print variables and jump to frames and jump to arbitrary threads that are currently running on the GPU side. It looks and feels exactly the same as usual, and that GDB also works with DDD. So you could use DDD visually to do it. Okay, so on Linux, that's how you would do it. How would you do it on Windows? Well, how do you debug on Windows? Obviously, you use Visual Studio. No, but obviously. So we're integrated into Visual Studio as well. So you use Visual Studio to debug on Windows. Okay, so you debug as normal, basically. Okay, now for the memory model annotations. So first off, And now I don't know, I'm going to really channel my SD1 chair hat. It is not salient what the machine does. The C++ memory model is the memory model of the C++ abstract machine. And you shall use it correctly, even if using it incorrectly does not result in failure on the box you're on.
What I'm saying is, when I go to Godbolt, for example,
Yes.
and I use memory order relaxed, I get
Yes.
the same exact code generated as if I'm using sequentially consistent. That's where I'm saying, like.
So not quite. I mean, it does generate. It has to generate mfence in certain cases. The compiler mappings are available on a website from the University of Cambridge. It generates mostly the same code. You are correct. It's not exactly the same code.
But on ARM, it's completely different. So
That's right.
On GPUs, does it matter, or is it mostly?
This atomic library does the right thing.
Okay. But performance matters if I use the wrong, or I can basically get better performance if I use the correct acquired release semantics versus just slap on sequentially consistent and everything.
Right. But I'd like to point out that the optimizer on x86 will exploit the freedom that you give it when you use the correct memory order. If you use memory order acquire, there's an optimization known in the memory model community as the Roach Motel optimization, which is operations can check in, but they can't check out. So if you have a critical section and it starts with an acquire and it ends with a release, operations before the critical section can actually be moved into the critical section, and operations out below can be moved up, but not the reverse, right? So that optimization is a valid and interesting optimization, even on x86, right? And so using the proper memory order always rewards you with the best performance on every machine there is. So yes, the step is a little bit bigger when you go to ARM and Power, and definitely NVIDIA GPUs. So yes, you have to use the right one. Our memory model, it would take hours to really get into it, but our memory model is in the vein of IBM Power. Hi.
The triple angle brackets.
Yes.
They take two things: the blocks and threads.
Yes, they take more things actually. They're sort of variadic.
So, do those have to be const expr, and what are they?
They don't have to be const expr. No, they're as good as operands to the function itself. So you could have just computed some value and pass it in. Yeah. What do you mean? What are they? They're unsigned.
What are blocks versus threads?
This is the High-Radix part. So we don't present a model of 163,840 flat threads. That's not the model. Threads are collected into blocks, and blocks can have between 1 and 1024 threads. And then we have waves of blocks are called grids, but they're invocations of a function. Okay. So when you say, you decide, do I want lots of small blocks or fewer bigger blocks to express the problem I'm working on? The trade-off is that bigger blocks consume more register file space. And so you might want a smaller block so that your threads can have more registers because we have a variable register architecture. It's one dimension. The other dimension is that threads within a block are guaranteed concurrent, and they're guaranteed to be able to cooperate on a problem. So if you wanted many threads to work together to compute a result, then you want those threads to be together in a block. So as you think about how you decompose your problem, you might say, I want 128 threads per block with however many blocks that means because I want more registers per thread. Or I might say I want 1024 threads per block because the cooperation between these threads is where the real value comes from. And but they'll get fewer registers.
Thank you.
Howdy.
Hi.
Now that we have starvation-free algorithms available to us on GPUs as well as lock-free algorithms,
Yeah.
what are the kind of big considerations that we should be taking with regards to boosting or sacrificing performance by choosing between the two paradigms?
Right. So it's it is not generally the case that lock-free algorithms are faster than starvation-free algorithms. It's an intuition that a lot of people have, but it's an incorrect one. Sometimes the lock-free expression of an algorithm has many more steps with memory barriers in it that you don't need to have there if you use sort of a low contention mutual exclusion scheme. In this case here, the reason we really got away with having mutual exclusion is because a radix 26 tree reduces contention real fast. You know, log 26 is a fantastic amortization strategy. So we had mutexes here and we survived because contention was low. Okay. There are other cases I can think of that have this attribute where I could write the lock-free one, but the lock-free one would have a lot more overhead. Okay, so how would you choose? I think you would choose the same. This is one of the things that I originally imagined it would not be true, but turns out is true, is you bring to it sort of the same thinking you would on the CPU, and it's all about contention.
Thank you.
Any more questions? Thank you.